Producing 10,000 ton of hot metal per day is a massive, massive achievement. But it's put your hearth under a relentless hydrodynamic threat. So as you are a senior process engineer, I have seen how high velocity of this metal many times due to asymmetric abnormal condition uh, end a campaign year too early. So we must have to, in such cases, we have to keep ourselves proactive. We must have to acquainted with the day-to-day activity, the database, the behavior of the trends, everything, and we need to also analyze the system in such a way to so that we can also correlate and diagnose what we suspecting. So on the slide you see a 3D cutaway of our active TiCN cell rendered in glowing blue crystals. So notice how they line the internal wall protecting the carbon brick from the carbon brick. So from the orange swirling iron pool in the center, this is what is just illustrated to show. So to the right, if you see, our HUD indicator show a stabilizing wear rate and a production target of 10,000 TPD. So by the end of this session, you will master 4 deliverables. So what are those deliverables? So the mechanics of the carbon erosion cycle, this is the first. Then the thermodynamics of titanium transport, which is very important. And the casting philosophy required for retention is supposed to be, I think, is the biggest, most important, because many times it is found that after applying the titanium as a source material from either briquette or either iron ore or through the PCI system, so many places. But many times these effects are not up to mark because operators don't have a clear cut idea about the its retention philosophy through the casting, and which is a very important aspect. So later on we'll discuss. And third thing is the mass balance math needed to validate our success. So this is also important because unless until we come across the data statistics, we cannot able to find out how much feedstock or again how much input we have to increase or decrease. So we are not just making iron, we are managing an asset's lifespan. So to stop the wear, we have to understand the 4 stage cycle that destroy our refractory. So coming to this area of destruction by the reasons are like this. So uh, um, mm, so 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 10,000 TPD operation having got a tremendous turbulent velocity in the elephant edge in the heart. So look at the left side of the slide titled the threat. You see aggressive orange arrow representing high velocity, and at this scale the sheer volume of the iron act like a sand blaster against your walls. Now follow the carbon erosion cycle flowchart. It begins with the contact first, where the molten iron hits the brick, and then move to the penetration where the uh, unsaturated iron enter the micropore. This lead to embrittlement shown by cracking the red brick, where structural strength drop and particle shear off. So finally we reach dissolution where the carbon simply washes away into iron pool. If your peripheral flow is stripping the wall faster than a shield can form, you are in a losing battle, or we are in a great danger, we can say. So we have to change the interface between the iron and the brick. So we do this by physically plugging those micropore with a renewable barrier, and this is what we have to learn how to build a physical barrier. So plugging the pores, we have two scenario here: an unprotected hearth on the left and a protected on the right. So in the unprotected block, look at the magnified crosshair. It shows micro erosion where molten iron snakes into dark grey carbon matrix. It is very clearly shown. Now shift your eyes to the right. These are the TiCN crystals plugs. They don't just sit on the wall, they form a physical dam uh, inside the bricks pores. So notice the orange line labeled 1150 Celsius isotherm. On the protected side, that isotherm is shifted significantly, significantly inward. So by keeping the structural carbon cooler, we lock out the liquid iron. So the operational impact is a massive reduction in chemical wear, effectively moving the erosion front from your expensive refractory onto the renewable titanium scaffold. So getting these crystal onto the wall require a two-stage thermodynamic journey, and those thermodynamics of TiCN we will look into. As we can see, the formation of titanium protection is a tale of two zones. So look at zone 1, the raceway highlighted in orange. So this is the engine where the temperature exceeds 2000 Celsius, and here the kinetics favor dissolution TiO2 from your ore is reduced and dissolved as a elemental Ti into the raising hot metal. Now follow that arrow to zone 2, the sidewall rendered in cool blue. So this is an anchor. As the metal approaches the water cooled hearth wall, the temperature drops below 1500 Celsius, and this thermal gradient trigger the precipitation of solid crystalline cluster. The so-what factor. So if your raceway adiabatic flame temperature is too low, you would not get proper dissolution. So if your cooling is too weak, you would not get precipitation. We are balancing a thermal blueprint to ensure transport and deposition. But thermodynamics only work if the chemistry dashboard is dialed in perfectly. So coming to the precision of the chemistry dashboard. So forcing precipitation, you cannot force precipitation. So without the right coupled reaction, as earlier also we come across that cooling should be intensive. So on the left, our titanium gauge indicate we need a least 0.074% Ti to provide the raw material that we have already discussed earlier presentations also. So in the center, the silicon gauge shows our essential driver. We need 0.42% silicon to help reduce TiO2 into the metal. But look at the red gauge on the right, sulfur. Sulfur is a thief. Sulfur is very dangerous as it take away the Ti. So, we say that the sulfur steals our titanium to form useless TiS, so wasting our expensive payload. So if your sulfur is high, you are effectively throwing money out of the taffel. So operationally, this means managing your slag basicity is just as important as the titanium injection itself. So you must lock in these dashboard parameters to turn that liquid Ti into a solid sealed. However, your even perfect chemistry will fail if your hearth hydraulics are not controlled. So coming to our this slide about the operator's dilemma, that is the raising rivers versus calm pools. So take a look at these two metaphors. On the left, we see a raising turbulent river. Just like ice cannot form in whitewater rapids, titanium crystal also cannot freeze if the peripheral flow is too aggressive. So on the right, we see a calm frozen pool. This is where the ice and our titanium shield freeze perfectly. So we can meet our titanium target and our wall temperature target, but the calm peripheral flow is operators dependent. Titanium require up to 6.5 hours of residence time to settle. If your cast house practices create a raising river, your protection will simply wash away. So this is where the manager, the shift in charges, or the expert of the furnace should have a philosophy on casting becomes and this becomes a dominant variable in the hearth life. So the primary tool for calming the river is managing your taffel length, which is first and foremost reason. So now coming to the controlling peripheral flow via taffel length comes into a picture. So look at the danger scenario on the left. Let me change the slide and as see. Now this is a very sensible picture where it shows that the danger scenario on the left, the short taffel. The red flow line shows fast, aggressive peripheral flow that has a lot of problems in the sidewall. So in this state, your titanium layer is constantly being sheared off, taken away. So now look at the ideal scenario. What is that? The long taffel rendered in cool cyan. So by maintaining a long taffel, we draw liquid iron from the center dead man rather than a periphery. That is the siphoning of the metal is a good one. If our taffel is lengthy, lengthy means it's an optimum. So this create a calm zone near the sidewall and providing the necessary residence time for TiCN to settle, to precipitate, to freeze. So operationally, the so what is that a short taffel is a death sentence for your hearth. So you must use high quality clay and disciplined drilling to keep that taffel long enough to draw from the furnace core. And that gives us a maximum scope to settle these precipitate, TiCN precipitate, and take away our campaign duration. So in a 4 taffel furnace, we can take this flow control even further with a strategic rotation, and which is very important to share with the audience. So the 4 taffel alternation strategy. So with the 4 taffel, we have a unique opportunity to manipulate the liquid flow. So look at the blue and the orange streamline. So by opening opposite taffel such as taffel 1 and taffel 3, we actually split the liquid flow. This creates a strategic low velocity zone between the taffel shown by the darker blue areas. So proper alteration can increase your titanium residence time from the 3.5 hour up to 6.5 hour in this zone. So this is where the silt grows the thickest. If you stay on the taffel too long, you create a permanent high velocity channel that erode everything in the path. So at 10,000 TPD, your tapping schedule is your most powerful tool for calming the river, calming the flow in the sidewall, calming the turbulence of the metal and slag in the corner of the top of the pad. So that we have got a minimum erosion, and because that corner is very sensitive, and these also allow the titanium beer to stabilize. So this is one of the example that when we have got a multi-taffel, how our main aim is to keep the peripheral metal and slag flow slower. So if we keep it slower, it will have got a better retention opportunity for TiCN precipitate. So but remember, you cannot protect the wall if the hearth is flooded. So that we have seen. So coming to our this hearth drainage slide, let me change it as yes, this is the slide, and you cannot protect flooded hearth that we have discussed due to these reasons, because it wash away all the precipitate, those valuable TiCN which we develop by putting in PCI or following through the briquettes, iron ore lumps. So many sources we use at a feedstock to create this precipitate. So follow this rate failure chain now. So poor drainage leads to dangerously high liquid level. So this forces erratic flow path where the molten iron is squeezed against the wall at the high velocity. So these causes wall scrubbing, scarfing we can say, so rubbing or which shears off your TICN layers. So look at the TI in the slag spike on the right. So when you see the titanium level rising in your slag, so it's a confirmation that your payload is being washed out, not retained. So maintaining a dry, highly permeable dead man is the foundation of all titanium retention. So if your hard drainage is poor, your expensive titanium injection is doing nothing but enriching your slag pile. So once drainage is stabilized, we choose between two methods of deposition and which are supposed to very important. uh, so coming, let me change. Yes, now our this slide, which is about execution strategy, that is prevention versus curative deposition, is a very good slide which shares valuable information. So as you can see that you must match the tool to hearth condition. On the left is a top charging or preventive tool. We use a low doses of 3 to 5 kilogram per ton. It follows the burden descent, has a long residence time and provide a global hearth-based stabilization. Now look at the 2-year injection, our curative tool. So highlighted in orange, this is for aggressive immediate response to localized hotspot. We use a higher doses of 6 to 8 kilogram per ton injected discontinuously during tapping. So note the location rules. You must inject 80 to 160-degree upstream of the active taphole so that the enriched metal washes over the damaged spot on its way out. So top charging is your daily vitamin. So injection is your emergency surgery. So this is how we can have a better understanding of the process. So regardless of the method, you must respect the physical timeline of the furnace. So coming to the our managing lag, the 10-day patience curve, and which is very important one. Let me change the slide. Yeah. So titanium deposition, as you can see, is a highly unsteady process. So do not panic or over inject. So look at this 10-day trend. The titanium concentration in the metal hits the 0.074% target round day 6. This is the chemistry lag breaking. But look at the hearth wall temperature. It stays high and erratic until the day 10. This is when the thermal lag break and the TICN finder stabilizes. So only then do you see your fuel and coke ratio drop as the thermal efficiency improve. So if you cut the injection on the day 5 because it is not working, you have failed a test of patience. The furnace requires a 10-day to reflect the new chemical reality in its thermal sensor. So to know if you are actually winning during these 10 days, then use the scorecard. So let's talk about this scorecard which is I'm going to open. Yeah, this is our scorecard, which is evaluating titanium mass balance. So as we pitching towards the wall, or is the titanium just washing out? So we use the fettling rate, which is also very important, and it's simply input minus output divided by input. So your input are TiO2 from sinter, pellet or injection. Your output are Ti in the metal and TiO2 in the slag. So look at the green zone. Where is the greater than 0? This is a patching. Titanium is successfully being retained on the wall. And if it is negative, so as seen in the red zone, you are eroding. So you must adjust your taphole length or drainage immediately. This scorecard is your ultimate reality check. It tells you if your precision chemistry is actually building a silt or just washing money. So let's see how this match correlate with the real world thermocouple data. So now coming to our next slide on the empirical validation. Uh, so as you can see, this slide shows the undeniable link between the math and the safety. These are your heart thermocouple over a 6-month period. This is the fettling rate. Notice the red vertical bar. Every time the fettling rate drops into the negative, we see a dangerous temperature spike shortly after. Now look at the green shade area. By sustaining a fettling rate above 30%, we trigger a safe drop where wall temperature parameter decreases and stay low. So, what it gives a clear indication? It gives us a clear indication regarding the maths, which translate directly into the directly this application into the thermal safety. So, if you sustain a positive mass balance, the thermocouple will respond. This what it means. So, this empirical data is why we trust the process even during the 10-day lag. And 10 day is the only best time to evaluate the effect of application, or we can say effect of this fettling. So this brings us to our final continuous loop of operational excellence, which is headed with the campaign extension loop. So heart production, we can say that what we have seen is not a one-time event. It's a continuous. It's a manageable cycle. And look at the infinity loop. It starts with a step 1, that is execute. So maintain your taphole length, inject upstream of hotspot. Moving to step 2, which is a condition. So look at your TI, titanium, silicon, sulfur dashboard targets. Then coming to the step 3, endure, that is a hold steady through the 10-day lag, that what we have discussed, and trust the thermodynamics. And finally step 4, which is about evaluation. So confirm a positive fettling rate and dropping temperature. If the shield is active, repeat the loop. So this cycle reduces your fuel ratio, lowers your temperature, and extend your campaign life by years. So at 10,000 TPD, this loop is the difference between a catastrophic breakout and a record-breaking campaign. So let's go to walk and let's applying in order to find out the effect.